Okay.
Yep.
Oh, yeah, there it goes. Okay, great. Yeah, I love computers, but I also love algorithms. And so what I want to tell you a little bit about is something that got me completely derailed from doing things I used to do with more hydrodynamics and MHD and radiation transport and doing lots of complicated physics, putting them together. This idea I want to tell you about is about understanding collisionless fluids in a novel way. And it fits, I think, very well with some of the M-body talks we've already heard about. Essentially, it's a technology that thinks of the M-body techniques that we've just seen in a different way. And so where I'm coming from is I sort of look at these cold dark matter simulations where the way we think about them is almost like star cluster simulations at the moment, where every single particle actually has the mass. It holds the mass, and then we apply some softening to try to avoid that these particles make orbits around each other, form planetary systems, and do any two-body effects that you would have. Instead, what you can do is take exactly the same simulation and don't think about these particles as where the location of the mass is. Think of them as massless tracers that are just some tracer particles that you picked out of that fluid, you gave it names, you gave it IDs, and those particles, all the mass is between those particles. So you just think of those particles spanning up a tessellation, some grid that then moves around, and so the deformation of your fluid elements is described by how these particles move. That's sort of the basic idea behind this, and I'm sort of starting out with my summary because I know we have very little time. What I'm going to show you, I'm not going to go through the whole list, just a very few things, is to show you what that way of thinking about M-body simulation is useful for. The very first thing that it's useful for is just analyzing an existing simulation that you have already. You don't have to do anything new. You have the IDs. You know where the particles came from, so that tells you how all that fluid has been distorted. It allows you to define velocities, velocity dispersions, measure, in fact, the velocity distribution function at single points. And so it gives you full access to the microphysical phase-space structure in your simulation. And once you have that, it helps you right away to sort of do better visualizations of your techniques because you now have an actual density field of the simulation. Once you have a better density field of your calculation, that sources the Poisson equation, right? So it's just the density field that, from which you calculate the gravitational potential, which you then, when you differentiate it, actually get much higher accuracy in your forces. And so that leads to a whole bunch of new methods that you can develop to do collisionless fluids. I mean, this can be plasmas as well as our particular case of the cold dark matter scenario that we're working out. It helped us solve a 30-year-old problem in where people had a hard time getting suppressing a pure numerical artifact where you had artificial fragmentation when you studied warm dark matter scenarios. It helps you to make gravitational lensing predictions from your simulations. All these density maps we've seen, right? Every single density slice for gravitational lensing, all you do is you do a two-dimensional Fourier transform of that to sort of see the deflection angles that density, surface density distribution produces. Now, if you don't have noise anymore in your image, you actually get much better accuracy in doing these predictions. I'll show a few examples about cosmic velocity fields. Just one very quick one on plasma simulations. And there's just, so it's been fun. It was like 2.5 years or so ago that I thought of this, and since then it's just been this gift that keeps on giving rather interesting results. So let me just show pictorially what this is. So this is a flashback to the 90s in a way. It's just a 256 cubed cold dark matter simulation. And the picture is just made by essentially nearest neighbor interpolation, if you want to think about it like that. All you do is you calculate the positions of your particles in this integer space that forms the image. If a particle is inside your pixel, you just add up the value. At the end, you do a logarithmic stretch on it, and it shows you the surface density projected through. And here is exactly the same data where we didn't do anything else other than think of the data in a different way. So let me just flash back and forth a little bit. And what you notice is, in particular in the low density regions, is extremely obvious, is that you just don't have any noise. There is no noise in the simulation. At this point, you're not Monte Carloing the density field. This is a full continuous density field that's always been in the data, and all it is a different way of thinking about it. No new algorithm. I mean, it's really just the way you make the image. On a very basic level, it's extremely simple to do this, because you start out most of your simulations on a uniform lattice. So you can think of every single bit of this Cartesian lattice that you have. You just have to tessellate the unit cube. There's multiple ways of doing it. We just chose here doing 6 different tetrahedra to represent one unit cube. All the edges here are just the simulation particles that you have. You know these simulation particles, they have names, they have your integer IDs, they move around. At any given time in the simulation, you write out one snapshot. From the IDs, you know, okay, that's that triangle or this tetrahedron. You just say, okay, where are all these particles? And say, okay, this tetrahedron is this big. It's like, okay, so that means this mass that used to be in this tetrahedron is still in this tetrahedron, but it's now stretched over this region of space. So when I make that image, all I have to do is draw a tetrahedron. And so on the GPU, we can do 1024 cubed type data interactively. And Rolf Gehler will show us a little bit, I think, this afternoon. But the fantastic thing is, instead of having all these particle plots, what you now can do is do a two-dimensional slice through the whole thing, and you start analyzing it, and it feels almost like you're dealing with a hydrodynamic simulation. You have access to all the data at any single point. So we can calculate the dispersion of the dark matter velocity dispersion at any single point. So this is just a two-dimensional slice through the most massive halo in the simple simulation. At single points, we evaluate the entire velocity distribution function. The full VDF, and here the 3 spatial components, that's the center of this halo. Looks close to thermal, but it's got non-thermal tails. Right? You know, I mean, there's many papers that devise entire algorithms that are trying to measure these things, to estimate phase-space densities, all these things. It's always been in the simulation data, and that's sort of the powerful thing of this whole bit. There's one particular example. Oh, that doesn't come out very well. It's a pity. So there's a warm dark matter simulation. I'm not sure. Well, you can tell that filaments here, very clumpy. Here it's totally sharp. It's hard to see on this projector. Fundamentally, in this warm dark matter simulation, all the clumping that you get when you do adaptive kernel smoothing is a pure artifact that you're using spherical kernels that you're using to visualize it. And that's how your code thinks about it too. It's spherical. You have a spherical softening length, right? It's just a radius at which your force law is modified. And so, but in reality, the fluid gets distorted and it gets sheared. And so when you have an isotropic kernel, you cannot represent this shearing unless you have many particles per resolution element, which is what the plasma community knows and has written mathematical proofs that you need hundreds of particles per cell or per resolution element to get any hope of converging. And the amazing thing now is, with our technique, it actually tracks this whole deformation. And you see, you get an excellent density field even at very relatively low resolutions. Okay, anyhow, you can tell I'm excited about it. Just a quick slice here. There's a cosmic velocity field, one component of the velocity. And the best technique we had in estimating what the velocity field is was this Delaunay tessellation approach, DTFE. But the problem with that one was it never could distinguish what is a bulk velocity from what is a dispersion. And so things were always really noisy, whereas in our technique, you now have a perfectly well-defined bulk velocity. Because what we can do is, so in this one-dimensional example where you have multiple streams overlapping at one point, since we identify all these streams, we can do the density-weighted velocity here, and it gives us the red curve. And that is the bulk velocity. That is the average velocity at that point. So you can get that completely right, whereas if you just tessellated it in real space, you would get this blue line that's all fluctuating. You know, one part is going that way, the other one's going that way, and it just mixes the two things. What is a dispersion? What is the actual bulk flow? And perhaps it's a bit academic, but when we calculate the divergence and the vorticity, all the old techniques always gave non-zero vorticity, even in the voids. And that's just mathematically impossible. You have a potential flow, it cannot generate vorticity, right? There's a scalar potential that is sourcing our forces. You cannot have vorticity. And when we do this on this phase-space sheet, it's identical zero everywhere. Even more so, if you look at the divergence of the velocity field, when you first create a velocity into a uniform grid and then do your differential operators on that, you get terribly wrong answers. Because this old technique, you see all the big features where you have all this amazing divergence right at the edges of the filaments. It's just wrong. It's the wrong sign, and it's off by orders of magnitude. And the point is you're taking differentials over caustics. And it's just mathematically, you're going to end up with the wrong answer. And it's nice, but this is a little bit academic at the end. It doesn't matter very much because velocity power spectra are volume-weighted quantities, and you're usually not very sensitive to this. It's just, perhaps I'm being overly tedious, but just sort of think about at least we now have a method that can do it correctly, and perhaps we'll find some good uses. So let me just say something about a computational geometry problem that came up in this context. Because we have all these tetrahedra, and we'd like to sort of grid that onto a unit grid sometimes to get a potential or for other applications. It's nice to have it on a regular grid structure. What we need to do is deposit tetrahedra into a Cartesian grid. And I thought this is a totally solved problem. It's been done many times. It was actually difficult to find. And so we took an algorithm from Franklin in '92 and generalized it so that we can now the 2D analog is putting a triangle into an image. And when you have the mass in the triangle, should also be then the total mass in the image at the end. So where you do simple things, in computer graphics, you know this as you have terrible aliasing. So the exact overlap is not calculated correctly. So when I integrate up the image, instead of 1, I'm off by a few percent, or just 1% in this example. We get a totally exact to machine precision. And that's even true when we have a linear gradient across it or even a quadratic function defined on this triangle. This works in any dimension. It works, we implemented it in 2 and 3D. It works for any polyhedra. It doesn't have to be a simplex. And the interesting thing is we never have to construct actually the intersection polyhedron. It's just an algorithm that sort of loops over corners and edges of the region, but never has to construct the thing. And so the first algorithm I wrote was just a very recursive thing. As long as the tetrahedron is big, make it really small, or divide it in half, and then you do this recursively until you can deposit it. This is 30 times faster. And the amazing thing now is when you take a crazy 16-cubed particle simulation, if we do the exact deposit with constant densities across the tetrahedra, you see already a big improvement. But now when you do a linear function on top of this, your density field becomes extremely smooth. And so now if you just think about very basics of numerical integration, what you're doing is we're going to integrate this field twice to get a potential, and then we're going to take a derivative to get the forces. So what we have now is a technique that can radically improve the accuracy of the force calculations. And I've seen amazing examples now in plasma, just a very simple one-dimensional case, where if you, where sort of this blue line is compared with this one over here, it's a good factor of 30 or so, 30 times fewer particles, I already have the accuracy of what the old method, or sort of a traditional particle in cell could have in 1D. So, for some 3D applications, you really want to think about this as a 30-cubed improvement in efficiency, getting down to the same type of accuracy. And yeah, so that's exciting. I think there's a whole roadmap where this is going to be useful for. And, I encourage you, I think a number of you here would sort of benefit, I think, or would sort of enjoy analyzing your data in this particular way. Thanks for your time.